We are here today to present our collaboration of Rutgers University and Bloom Energy, optimization of three-phase grid-timed inverter systems.
Bloom Energy is an innovative company dedicated to producing clean and cost-effective energy solutions. They've created a unique on-site power generation system called the Bloom Box that utilizes innovative new fuel technology to produce power practically anywhere. Bloom boxes are essentially power plants in a box. The way they work is that they have thin fuel cells which take in oxygen on one side and fuel on the other, and these are bundled and packaged into an outdoor safe case. Fuel being oxidized in these cells creates electricity.
This design is extremely advantageous because there is no need for burning, combustion, or power lines from an outside source. Bloom Energy hopes that one day these Bloom boxes replace the electrical grid altogether. Before that happens, though, there are some challenges that need to be faced.
One of the most pressing of these challenges is the need to optimize efficiency of the grid-tied inverters that complete the DC to AC conversion process. This is the process that essentially enables power to be fed back into the electrical grid from the fuel cells. This is crucial to save on valuable energy resources and money.
The primary objective of this project was to create and implement a theoretical model of a single three-phase grid-tied inverter control system from a real and reactive power feeding perspective. In simpler terms, our project involved designing, simulating, and analyzing this inverter system and creating a controller to minimize the power loss in the DC to AC conversion. These theoretical findings can be used to create control systems for multiple grid-tied inverters. The simulation and analysis portion were completed using Simulink to model the system and collect its data.
We built a model that can simulate the effects of load changes on our inverters. Our objective is then to develop a controller that can use the feedback from the utility side and from the output of the inverters to then change the simulation characteristics of the inverters as to avoid loss in transmission. Now, our simulation starts with a 40 kilowatt stack of fuel cells, which then goes through a DC to DC converter, which then after that goes into our inverters. Our inverters are three-phase 6-pulse inverters. Then it goes into a LC filter and a model which takes the voltage and current and feeds it into a controller, which then sends the 6-pulse signals into our inverters. After, it goes into our load, and then it goes into a step-up transformer, which changes the voltage to simulate a utility voltage line, which then goes into an infinite bus.
Here are some graphs indicating the results of the simulation that Pat just described. You can see that real and reactive power measured at the utilities stabilizes after a certain amount of time. There and there. This is most likely due to the fact that the controller is stabilizing the system.
The controller for multiple inverter systems can be designed using the drip control structure. In drip control, inverters are connected in parallel to provide system redundancy and high reliability for high power application. By using the drip control method, we can effectively limit the deviations in frequency and voltage within a certain margin. This structure also allows active and reactive power to be shared equally.
Future plans for this project include implementing the theoretical model of the single three-phase grid-tied inverter system on hardware provided by Bloom Energy, and applying findings from this project for multiple grid-tied inverter systems using the drip control structure. We also plan to publish our findings with our supervisor, Dr. Hana Godrich. At this time, we'd like to thank the following people on this slide. Thank you for watching.